to do. Let me make sure I kept it open. If I did, nice. All right. So the last thing we did was we got a tangent line of this polar function. Remember, all we had to do was get the x coordinate, get the y coordinate, and then get the y dx, which was this big mess, but with like hopefully not super hard. And then we just put it into the formula that we already know from way before. And then I gave you a preview of what's coming today is like sector areas that we're going to get. And so integrals will use this formula rather than just function d theta. So here's an example. Well, let me just make sure I don't want to say anything else. Oh, yeah. Yeah. So most of these that I've seen on the test are like on the calculator, like on the AP test, are on the calculator section. But if you were in a college class, you'd probably use these formulas. So I'm going to do one. The first one I'll do with like by hand by doing this little formula. And then the rest we'll just put in the calculator. Also, I think the way I use the formulas or the way I have seen these, you may see these as 1/2 minus 1/2 cosine of 2 theta or 2x, whatever. Or you may see these like this written somewhere else. So like if you put these into Photomath or an integral calculator or something like that, you might see any of these equivalent forms of that. I think I like to use this one. Okay, and then obviously same here. And then the tangent one doesn't really come up that much. So I would say if you're going to worry about two that you might learn, do the sine and the cosine one, because they're the same thing. It's just the sine is 1 minus cosine and the cosine is 1 plus cosine. To me, that makes sense in my brain because I'm like, oh, okay, the cosine should be the positive cosine, and then the sine is the negative cosine. I don't know. Like that's how I organize it in my brain. But if you don't remember this, like I said, this doesn't. You don't need to know these on the test. I'm talking. All right, cool. So this example says find the inner loop of this function, and then like I told you guys, a lot of the times the graph is provided for you. Okay, so here's the little picture. Here's the graph we're trying to get, or like the area we're trying to get. So of course we're going to set up some sort of integral, and then remember the integral is just going to be the function like this. Like that's the temptation because that's what you've always done is to get the area of your curve, but it is 1/2 r squared because of the sector thing we talked about yesterday. So 1/2 times this function squared. And then you just have to figure out from where to like set up your integral. And in this case, it's given for you 2 pi over 3 to 4 pi over 3. But let's pretend it wasn't. Here's me crossing this out. Pretend this wasn't there. Do you have any idea how you might find out from where to go? Hey, yeah, good job. That was really quick. I thought you guys might think about it for a little bit. But yeah, this inner loop happened when I made the graph and I went cross 0, made the inner loop, cross 0 again. So the 2 times that I crossed 0, that was the start of the inner loop and the end of the inner loop. And a lot of times that's the idea is find out when the graph crosses 0, and in a lot of examples they'll ask you like find one petal of the flower, find the inner loop of this, or find the outer loop of that, and all of those things have to do with when the function is 0. Okay, so if they didn't give you those, then you'd say 2 plus 4 cosine of theta equals 0. You'd solve this. Which means cosine is negative 1/2. And then that tells you on the unit circle that's negative 1/2 here, and it's negative 1/2 here, which is 2 pi over 3 and 4 pi over 3, which is the things that they gave. Okay, so 2 pi over 3, 4 pi over 3. There you go. And then we do that integral. And actually, I forgot I said I'd do this one by hand. So let me make this small and put it up, get it out of the way. So, okay, well, that's out of the way. Okay. One thing that maybe I should mention is if you get 2 pi over 3 and 4 pi over 3 and you're not sure, like, oh, am I sure that that's going to be the inner loop? Then this is what I was talking about yesterday, is you could take numbers between 2 pi over 3 and 4 pi over 3 and make sure that the graph aligns with those numbers. So, like, for example, if I take what's somewhere between there, like pi, for example, if I take pi, does that make sense that that's in the inner loop? Let me check. If I put in a pi into here, that would be 2 plus negative 4, which would be negative 2. Oh, yeah, that makes sense because when pi is here, a radius of negative 2 would show up here. Yeah, that makes sense that that's the inner loop. Okay. And then if you're still not sure, plug in more numbers and verify. But in this case, I think I'm convinced. Let's do the integral now. So watch this. 1/2 times integral of 2 pi over 3 to 4 pi over 3. If I wasn't here in front of you, what would be your first instinct doing this? Yeah, me too. Yeah. Yeah, unfortunately, I don't see some sort of U substitution trick or something that we could do to get rid of the squared. The only thing I see is like expand that whole thing. So if you FOIL these out, you would get, remember the shortcut is this number squared plus 2 times 4 cosine, but times another 2. So that would be 8 times 2 is 16 cosines. And then plus this number squared, so 16 cosine squared. Okay. Okay, and then some of these you know already. Like what I'm saying is, if you look at these functions, I know this antiderivative, I know this antiderivative, and this antiderivative is what I'll use these formulas for. So that would be 1/2 times. Let me just take these red ones right now. 4 theta plus, right? Yeah, plus 16 times theta evaluated at 4 pi over 3 and 2 pi over 3.
Why is the sign positive?
Am I wrong? Because it's the antiderivative.
Oh, I see. Yeah. Okay.
Yeah. This antiderivative. That's just those two, and then I still have to take the integral of the 16. So that's going to be more involved. Okay, but the 16 cosine squared. Yeah. And watch this. So there's a lot to keep track of. But the 16 cosine squared, I'm going to use this formula for. Let me use this nicest version, I think. This 1/2 times 1 plus cosine of 2x. So I'm going to replace the 16 cosine squared with 1/2 16. Or like 1/2, or 16 times this. Okay. But, and that's exactly what I was going to say. Don't forget there was a 1/2 in front of the entire thing. So this dude already has a 1/2 in front. And I'm putting an extra 1/2 from the formula in there. So that's 1/4 16 cosine squared. Or actually, let me do it like this. I have the 16 in front and the 1/4 up there, so I can make this a 4. Just to not do too much, let me do 16 4. I've already written all that. And then the little formula 1 plus cosine of 2 theta. What's up?
I was just gonna wonder if we're like once we get to the expanded equation before we take the integral of anything, couldn't we could just take out a 4, right? Because that's
Yeah, that would have been good as well. Yeah. all these have a 4, that could have made this one half nicer. Yeah, that would have been a good idea. Good job. Okay. All right. Now, okay, on this side, we could plug in the 4 pi over 3 and the 2 pi over 3, and both of these make it really long, etc. Let me save that for last. In fact, I think I'm not going to do that, and I'll just tell you what the answer is, because I know you're fine at plugging numbers in, and I don't want to be looking at much space I have left. So I don't want to be writing a whole ton. Let me just keep this as this times 4 theta plus 16 sine of theta at 4 pi over 3 and 2 pi over 3. Boom. I'll mess with that later. And then this, I'm going to write as 16 over 4 is just 4 times the antiderivative of these. Antiderivative of 1 would just be x normally, but this is d theta, so d theta. And then antiderivative of cosine of 2 theta, do you know that one? No, that's too much. But it does have to do with the 2. No,
It's 2
times
2 sine of the same.
It's 2 sine theta.
2 times 2 theta.
2 theta.
2 sine of 2 theta is almost it, except you guys are taking the derivative. You're doing derivative of cosine times derivative of the inside, which is kind of right, except instead of here, let me just write it. Okay, sine of 2 theta, but if I took the derivative of this, I'd get cosine of 2 theta times the inside function times 2. So let me counteract that times 2 by dividing by. So yeah, technically somebody said, oh shoot, it's U substitution. Yes, technically it is U substitution, but I did it in my brain. Or in other words, if you see like some sort of linear inside function, then you can skip the U substitution and instead of multiplying by the inside derivative, divide by the inside derivative. You're taking the antiderivative. Okay, and then plug in 4 pi over 3 and 2 pi over 3 for that as well. And then that itself is a big long mess, but that's not the part I was worried about. I was worried, like, let me let you guys see one time where I used this little formula. Again, on the test and in this class, you only, I've only ever seen it in the calculator section, so you don't even need to do that. But in a college class, I think you would have had to do that, like by game. And so if you did plug in all these numbers and combine like terms, take the sign of that and all that stuff, you would have gotten an answer of you would have gotten an answer of 12 pi over, oh, that's just 4 pi. But still, I'll just write it how I have it. 12 pi over 3 minus 24 square root of 3 over 4. Oh yeah, both of those are divisible. Yeah, that's my fault. But I was so tired of combining like terms and stuff that I said I'm gonna leave it there. Yeah, both of those are actually way nicer. 4 pi minus 6. Yeah, true. Good job. Okay, so all of the antiderivatives made it look more annoying than it was, but really the setup and the new stuff was pretty easy. Find out where the inner loop is defined, 2 pi over 3 to 4 pi over 3, and set up the integral using 1/2 r squared, not just r d theta. Cool. Okay, so then next one will be kind of similar, but I think it's like an inside and outside. And I don't think I even need to teach you this. You probably already know. Take the area of the outer one minus the area of the inner. Okay, so here's the example that they gave us. 3 plus 2 sine is the blue function, and the red function is r equals 2. And it says get that green area inside this one and outside that one. Okay, cool. So I know it's going to be some sort of integral of x. This function minus this function. Except don't forget, this isn't like the other ones. This is polar coordinates, so it should be 1/2 function squared minus function squared, like I said. Cool. All right. And then from where to where am I going? Oh, shoot, it didn't tell me. So do you have any idea how I'd find out? Is that a hand? How? Yeah, okay, good job. Yeah. I just need to find out where was this angle and where was this angle where they intersected. And then I just go from this one, boop, 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 all the way to that one. So that would be 3 plus 2 sine of theta equals 2. And I solved. Okay, sine of theta negative 1/2 would be here and here. Which would be these big 1, 2, 3, 4, 5, 6, 7 pi over 6. And 11, yeah, 7, 8, 9, 10, 11, yeah, 11 pi over 6. And if you need a reminder of how the unit circle work, then come see me in advisory or something and I can do it. You can see it comes up a lot, especially for you guys BC. Okay, so there's my 2 1s. But watch this, watch this. 7 pi over 6. 11 pi over 6. That is wrong. What? What? You tell me why.
Oh, because it's getting close to the area.
Yeah, circle don't meet the original. Like subtract too much.
Because it's under negative, right? Like
So
negative,
maybe-
that's positive.
Like, would you make 2 and 3, like, that the one would be like, the area of 2 for 1 is whatever, is that 2?
No, you get no. The problem isn't what we're subtracting. The problem is with our bound.
Oh, it's inside, it's getting the inside, not outside.
Yeah, that's the thing. That's the right little gesture. Is that we put 7 pi over 6 to 11 pi over 6. This is 7 pi over 6, and if I rotate to 11 pi over 6, that's this one. Ooh, that'd be getting. I don't know how to show it.
It's negative 6, 7.
Good job. Yeah, exactly. Instead of going from here to here, you have to go from this dot to that dot. And if you said 11 to 7, then that's wrong because that would be going this way. So yeah, you have to think, oh, what's another way to say 11 pi over 6? Oh yeah, that's negative pi over 6. And then that goes around you this way like the unit circle does. 7. Nice. So we go. Okay, the correct one would be 1/2 negative pi over 6 to 7 pi over 6. And then okay. And then this one, if you really had to do it by hand, you would expand all that combined length terms, use the formula like 1/2 times 1 plus cosine of 2 theta, like we did in the last one. But like I said, I think most of the time you'll see this on the calculator bit. And if you put this into Desmos or your calculator, you get 24.1870 calculator for those checking ones. Yes.
I was gonna check if my computer died. Can you just, or like, since you have like Desmos or whatever, would you just plug in the first 2 equations to see like where the 0 is or whatever,
Oh,
and then and then just plug in those to like the bound integral? Or would that not work?
oh yeah, that would work.
Although you still need to like know that are like negative.
Well, actually, I don't know. I didn't try that. I don't know if it tells you an X coordinate, Y coordinate, or if it tells you R theta. Nothing. I guess you still have to find that by hand. But what you could do is put X's in here, like Y equals like this. That's a smart idea. Y equals 3 plus 2 sine theta, or 2 sine x, I guess, but it's still understood what I got. Y equals that, and Y equals 2, and then that will tell you when it intersects. Nice, yeah, that's a good idea. I didn't think of that. Nice. Yeah, that'll save you some time. But in case this is like on the like, if they put this on the multiple choice no calculator, then they might ask which one of these integrals gives you the right thing. In which case you wouldn't have a calculator, but you wouldn't have to do this by hand. So it's still good to know how to do by hand, but that's a really good idea. Don't waste your time solving it yourself. Nice, Ian. Yeah. All right. And then any more questions? Okay, last one is the same idea but backwards. Now get the area down here.
You have to go into polar coordinate section. Then you can like see where. That might
7, 5, or 6. Yeah, right.
You have to go into the polar.
Oh, I forgot that was even an option. Yeah, that's worth saying. Look at this, you guys. Look at this is in here. Let me turn these off. Go back to the polar ones. Desmos has a setting where you're in right now in rectangular, but if you go to polar, I don't know that it tells you, but it shows you a little bit if it's a nice number, 11, 5, or 6, and 7, 5, or 6. Nice, you all are forgot about that. Good job, you guys are teaching me. Okay, this one, like I said, it's the same functions, the same intersection points. Now I want this bottom bit. So, like Annika said, now I'm just going to set it up the same way. Well, kind of the same way, but going from 7 pi over 6 to 11 pi over 6. Now I do want this bit. So it would be 1/2, don't forget that, 7 pi over 6, 11 pi over 6. And then, but what's different about the last one? Yeah, exactly. Now the outer function is the red one, the inner function is the blue one. So it would be 2 squared minus 3 plus 2 times 3. Boom. And put that one into your calculator, you get 2.1958. Nice. All right. And then that's all I've got, but let me keep talking to you guys because if we want to get I want to get done with your curriculum with still some weeks to like review. Because if the last day you learn unit 10 is the day before the test, then you're kind of in trouble because you never get to check. So according to my schedule, we can be done 2 weeks ahead of time if we start 10-1 tomorrow, like or whatever, Monday. So that's what we'll do Monday. But I also don't want you to be like learning thing after thing after thing and never getting checked if you know that. So I was thinking in class on Tuesday when everybody else is when the AB people are doing their independent work, I might give you a test for this. You know what I mean? And it shouldn't be like a stressful, like, oh shoot, this is gonna impact my grade, but treat it as if it was. So I would do your homework over the weekend on Monday, Tuesday morning maybe, and then Tuesday come in and treat the test like a real test. I'll grade it and I'll put the scores in the grade book, but there's a way to mark it so it doesn't impact your grade. Yeah, but then that way it's like as real a test as it can be, and you can check how much you learned and all that stuff.
If it affects your grade in a good way, could you unmark it?
I don't know. I guess you guys are doing extra work.
But
that
extra
other people-
credit,
Yeah.
Just give us that
I mean,
credit.
it's like extra credit. and it's available to everyone if they want.
I'll think about how, but now that you said that, first thing that came to my mind was I could do like, if you get between 70 and an 80, 1 point of extra credit, 80, 90, 2 points, etc. I'll think of something like that.
Oh.
Yeah, 1 point or 2 points of extra credit. Extra credit does so much for your grade that might be good.
Wait, do you have any extra practice? I think I lost my homework.
Yeah,
Are we done?
yeah,
We're doing transport final.
yes.